Okay, so today we have this topic from probability that we need to do some things in the course next. So this is on multivariate transformations. I didn't think I spelled this right. Multivariate transformations. So I have a jointly distributed or n random variables, and I want to make a transformation on all of them at once. Okay, so what is the new distribution? Well, we'll have to see this through examples. I'm not going to do a proof of the formula for this, so instead I just try to motivate it a little by reminding us of the single variable case, which we can do a proof for, and then see how it looks a lot like the bivariate case. And that will do it for this lecture. It'll probably be 2 parts, maybe 3 parts. Let's just review if I have one variable then. And we're talking about continuous random variables throughout the discussion, although we can do this for discrete ones. Well, they might not be computationally easier all the time, but theoretically they're easier to understand, I think. Either way, we're just going to focus on a few continuous ones in today's class. So one random variable. So suppose X has a PDF F sub X, and we use this word support. Has support A, it just means that this is the set on which its density is non-zero. And then say I have G of X is some either strictly increasing or decreasing function on A, and I assign Y to be the name for G of X. Lots of examples of this. Then this is the PDF of Y. Okay, it's given by this formula. Looks a lot, looks like the chain rule basically, right? So it's, but this is the, this is it. Okay, so I'll show you this now, why this is it, and then we'll see how this form extends when there's more than one variable. The support for why this is not terribly revealing here. It's just, of course, if y is g of x, then any point in A gets mapped to some point, and we're calling that collection of points B. Okay, so why is this true? So just, you've done this probably. So suppose, so to show this, suppose G is increasing on A, then probability Y equal G of X less than or equal to little y, say, is just equal to the probability increasing function, right? So G inverse, sorry, X is less than or equal to G inverse of little y. Okay, then this is just the CDF of X evaluated at G inverse of Y. So this is, okay, so we could write this like with the capital F notation or not. Let's just do it. So Fx G inverse of little y. I can take the derivative then of this, and I get Fy of little y, right? So this probability is Fy of little y. Okay, so then this is just d dy, which is d dy of this. time, and then it is the chain rule, right? So this is just fx g inverse little y times the derivative of g inverse little y. One thing to notice here is that this being a PDF is greater than or equal to 0. And this this is an inverse here. This inverse function is greater than 0, right? Yeah. So so this is greater than 0 because g is increasing. And this is greater than 0 because it's a PDF. So it's so the whole thing's positive, right? So the PDF's positive, thankfully, right? And we can write it just like this. If g is decreasing, can only be increasing or decreasing by what we said at the beginning, that we're forcing it to be one or the other. Then it's almost the same, but you just have to deal with the minus sign. Y equal g of x less than y is equal to probability x greater than or equal to g inverse of y, which is equal to 1 minus fx g inverse of y. And so fy of y is equal to the derivative of this, which is the derivative of this here. And what do we get? We get a minus sign, we get fx g inverse of y, and then we get times d dy g inverse of y. However, now this is negative, right? That's less than 0 because g is decreasing. And so I get a negative sign, another negative sign. So again, it's positive as it needs to be, and everything's okay. So in other words, we can easily write this then for either case. So conclude fy of y is equal to fx g inverse of little y times absolute value d dy g inverse of little y for any monotonic g. Okay, could do some example here, but I think this is enough because we did this basically in probability, and I think we don't really need an example. Instead, let's go to now the bivariate case. Okay, so now we want to consider, so step 2, not that these are actually any kinds of steps or anything, we're going to consider x and y, 2 variables for a random vector, and we're going to make a transformation on them. So we're going to have a equal the support for the first one, let's say x little y, such that the joint PDF is non-zero. And we'll have some function on x and y that will give us some new variable u and v. So we'll let b equal, very similar, b equal the set uv, such that yeah, u equals, say, g1, V equals G2 for some X, Y, and A. Okay, now I can't talk about increasing and decreasing here in the same way. So, well, first let me finish this. So when we have this set up, we have, what do we have? We have F, U, V. I didn't even actually write the first thing down, which I should write, is greater than 0 on B, right? Sure. So what is this? I am talking about taking X and Y, random variables with joint PDF. And then I'm setting U, making a new random variable, a new pair. U equal to G1 XY, V equal to G2 XY, and I am finding the density of UV, right? And letting denote the joint density. Okay, so if I do this, I simply have to replace the monotonic condition with a one-to-one condition. This is the simple case. Doesn't mean you're dead in the water if you don't have things that are monotonic or one-to-one on the whole set, but this is the starting point. Okay, so we'll talk more about that in a second. Those are other cases, more complicated cases, but essentially things can still be okay and usually can be dealt with. So let's let's see here. So what is the new thing? We want just injectivity, right? We want one-to-one. We want one-to-one. Okay, so let's say let's assume this map. So or this R2 to R2 function, A to B is one-to-one. And so that means they're inverse functions. So there exist we'll just call them H1 and H2. Finding them is another question. Also, because of the formula, you're going to see they need to be differentiable, at least most places. And there's a lot more, but just to get us going, a lot of the cases we want to do fall into these simple cases. And so that's fine. So then here's our result then. This is the thing that's supposed to look like the other result for one variable. We have F, we want the density, the joint density for U and V, then FUV equals, well, do you remember? Let's look up here. Fy, the new variable that was made, that was G of X, is F of X evaluated at G inverse of Y. Okay. And then I take the absolute value of the derivative of the G inverse. So this is going to involve H1 and H2, not so much G1 and G2. So I'm going to have Fx y. And in here, I want X. That's what Fxy understands. So I'm going to have it in my new variables. H1 UV, H2 UV. And this is perfect so far. And then I want times the derivative of the inverse image. So the inverse map. So we're going to just, and I want the absolute value of that. So we're going to call it J, and then we'll just define J to be, it's just the determinant of these derivatives. So, or these partial derivatives. So dx du, dx dv, dy du, dy dv. So remember, the determinant is just dx du, dy dv, minus dx dv, dy du. And here, when I say x, what do we really mean? So we really mean where dx du equals, well, what was the map back to x is h1. So this is just the h1 uv function of u and v du, etc. Right? So for the other ones would be like this too. And I want the absolute value of this. This could be negative or positive. I want the absolute value. Certainly don't want it to be negative, right? If I have a density here, and it's correct to take the absolute value of it. Okay, so this is the formula. It's supposed to look like the one-dimensional case, and this is supposed to at least help you remember it. But if you want to understand this more, you should look at a good book on multivariable integration or vector calculus. I like the book by Marsden called Vector Calculus. This is in chapter 6.2 of that book. So you can see Marsden, Vector Calc. I'm not really sure the edition, but I think the recent edition is chapter 6. Okay, let's see. So we should do some examples with this. I think, let me see how much time. So we'll pick up with the example in part 2.